Question 11. Draw an arrow to indicate the direction of the force on this particle due to the electric field. Now we have a positive charge. What does that mean about the direction of the force? Is it in the same direction or the opposite direction as the field lines? That's right, it's the same direction. We always draw electric field lines based on what the positive charge will do. Question 12. Draw the electric field in this situation. We have two positive charges and one negative charge. Now we know that the field lines of the electric field will point away from the positive charges and towards the negative charges. So drawing lots of arrows pointing into the negative charge and lots of arrows pointing away from the positive charges might give us something like this. So your answer should look something similar to this picture. We can see that the positive charges always have electric field lines pointing away from them, and the negative electric charge always has field lines pointing towards it. Question 13. If an electric field has a strength of 200 newtons per coulomb, what is the strength of the electric field in volts per meter? Now this is something like a trick question. It's asking you to compare volts per meter to newtons per coulomb. But as I've mentioned before, these two ways of measuring the electric field strength are exactly equivalent. So the strength of the electric field in volts per meter is also exactly 200 volts per meter. The units volt per meter and newton per coulomb are equivalent. They mean exactly the same thing. Question 14. A uniform electric field points from right to left. Two electrons are placed next to each other in the field, so one is on the left and one is on the right. Compare the strength and direction on the force on the electrons due to the uniform field. So we can ignore the force due to each other. Alright, so let's think about this. We have the electric field pointing right to left in this direction, and we have two electrons. Now, how do we determine the strength of the force in the electrons? Well, we use this equation, F equals QE, right? Remember that one? Now, the charge on each electron is going to be exactly the same, so Q is constant. The E on each electron is going to be uniform. It's always going to be pointing right to left, and the question in fact says that it's going to be a uniform field, so the capital E is constant. That means that the F must be the same for both electrons as well. So now all we need to do is write down this answer. The field points from right to left, so positively charged particles would move right to left. That means that the negatively charged particles have to move left to right. Negatively charged particles move in the opposite direction to positively charged particles, which means they move against the direction of the electric field. The strength of the force on a charged particle is the product of its charge and the electric field strength. And in a uniform field and two particles with the same charge, the force will be exactly the same. Question 15. Classify each of the following as scalar or vector quantities, justifying your answer. A. Electric charge. Now, is this scalar or vector? Remember that scalar quantities can be represented by a number, but vector quantities have to be represented by a number and a direction. So in the case of electric charge, all we need is a number. So it's a scalar. It's either going to be a positive or negative number, and it does not have a direction. What about electric field? Can this be represented just by a positive or negative number? No, in a diagram, we have to draw it with arrows. That means it must be a vector. So an electric field is a vector because it has both strength and a direction. It'll always point in the direction of that a positively charged particle will move, which means it points towards negatively charged particles and away from positively charged particles. So that's the end of the questions. In this section, we've learned about electric fields, what they are, and why we're useful. Electric fields are a very useful tool for thinking about electric charge and how it affects other electric charges.